In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality.
All right, hello and welcome, lads and ladettes, to Celestial Theodolite update number 30. Last week we left off with discussing the timings of the geometric intersections, in which predicts the earlier intersection timing versus the later, and to give an explanation as to why. So everyone's had about a week or so to think about it. But before we get to that, I do want to cover a couple of things spreadsheet related. Give me 1 second here. So special shout out to Embo, who's been going through the spreadsheet, and he pointed out the difference in spherical trig versus the Euclidean projection of a central angle, which is what we're using. Now, they are equivalent for all intents and purposes that we're using, but the fact of the matter is that the angles that we're using will always add up to 180 degrees, whereas on the globe, with spherical trig, it'll always be in excess of 180 degrees. So there was an error there in the derivation for the globe angle, but it was at the decimal placeage of like six or seven decimals back or whatever. But anyway, I did change it to use Embo's equation for actual spherical trig, where the angles would add up to over 180 degrees. And the difference between those and the Euclidean projection are given down here. And like I said, the differences are outside of the arcsecond range here. You only need, I think, to the fourth decimal for arcsecond agreement, and we're in like the sixth or seventh. So everything is all good on that, but there was a quick update. But shout out to him for going through it and pointing that out. That is an important distinction to make. So shout out to him. Okay, so last week we were going over this animation here to represent the time. So I wanted to kind of back it up and give some significance to what's being shown here. So in the spreadsheet, we have the time of occlusion, all these angles, right? But the big things to take away here are the intersection differences between our predictions. Because when we go back to derive an elevation off of the occlusion angles, there's always an error. So and same for the distance when we derive the distance. And the same goes for the globe too. But what's the source of the error? How can we simplify it? Well, the error comes from the difference in what was the intersection difference between what we predict versus what was measured, and same for the globe. So when we reference the true position with respect to the peak at the time of occlusion, we get 2 arcseconds in difference. And for the globe, being the observer-based prediction, where the star has already, should have already geometrically been at the angle 217, and now it's at 206 when the occlusion occurred. So they missed their 217 occlusion or intersection window by 11. So when we go on to derive things, this is why the globe is off by that amount, because that's the angle that they're using for the occlusion, and same for flat Earth. So this is what the stem of the error comes from. And this comes from the fact that the stars are lingering, right? They're not following the 15 degree per hour relationship. And there's no real way to account for that other than, just saying refraction. But this is the difference in following the actual celestial sphere. And I'll see if I can pull up a screenshot of what Brian mapped out for that. But the important thing here is that on this spherical coordinate system, if we take a slice of this circle here down to the radius, we have 2 points that subtend the circumference of the circle here, right? And these 2 points that subtend the circle is called the arc length. And that arc length is proportional to a distance. And you can do that by multiplying out the radius. So I added this here for a little explanation slash, just sanity check, really. But here we take Earth's radius times gamma, and gamma is just distance divided by radius, and that gives you an angle in radians. You can convert that to degrees, which I do in this formula here. And then so all you do is just multiply radius by the central angle, and you get the distance back. So it's pretty straightforward, nothing too fancy, but it's just to show that over this distance here, over this arc length of 27 arc minutes is equal to 50,000 meters. So the distance between the observer and this mountain, 50,000 or 27 arc minutes. So if we go back in time, and we know how fast the star's true position move at 15 degrees per hour, as per the model says. So we know how long it'll take this star to traverse 27 arc minutes in angular difference in the sky, and how long that'll take. So at the end of this arc length, at the end of this 27 arc minute angular drop from its original position here, if we rewind the clock by 2 minutes and 29 seconds, the start of this star at 18:40:38 for the observer, the true position is at 2 degrees 33 arc minutes. And with respect to the peak, it's at 3 degrees. But we need not be concerned with that yet. So anyway, as time goes on, so the drop over distance of that arc length is this half gamma here. So gamma divided by 2, whatever the central angle is, just divide it by half, and that's how much drop over distance there is as an angle. And then you just multiply that by gamma to get what it would be for, or actually it's slightly different for that. There's a couple different ways you can get what it would be. You can also just do a tangent or whatever to convert it back. But anyway, you just do whatever function you need to get to convert this from arc minutes into meters, and that will convert the drop over distance from an angle into what it will be in meters. And it's always proportional in that way. So at about halfway, at a minute and 15 seconds of its 2 minute and 30 second or 2 minute 29 second transit, it's going to have dropped 13 arc minutes. And then a couple arc minutes after that, it's going to intersect with the peak. I think this puts it at like 219 here at 115. So if you add 115 in time, and this is all added on my new, I made a guide to walk you guys through this right here. I'll put a link in the chat. Why the globe predicts an earlier time, geometrically speaking. So there it is in chat. All right. So anyway, when we, it comes out to like 219 there, and then about 40 seconds later, it ends up at 217, and this is its intersection point where it should have intersected at 218:42:04 is when the globe had its intersection time. So right here, if we rotate the, where's the one that makes it do the thing I need it to do? There we go. Okay, so we started here. It's been about a minute or so, little over a minute, like a minute 30. The intersection for the globe occurred right here at 218:42. Now, the star didn't, no occlusion, no geometric occlusion yet. So a little more time goes on because it still has to traverse this central angle. So our intersection differences added up together and as a time converted. So 1 minute, 3 seconds plus 114 there is if you add that to the 115 for the drop over distance in time, you get the full central angle here of 2 minutes, 29 seconds of real time. So this is how all of this is related. So as more time passes by, it gets occluded within 11 seconds of what Flat Earth predicts, real time. And the angular position difference of that comes out to be 2 arc minutes. So the starting true position was 233. The ending true position for the observer was 233. Now, the globe's chance for a congruent triangle from observer to peak to star would have been at 217 or thereabouts, right? The same way flat Earth is a little off, the globe would be a little off like that too. But otherwise, the so like basically the error should be reversed. But what happens is the star gets geometrically occluded when it finishes traversing that central angle. It takes the full 2 minutes 29 seconds to complete that central angle before it gets occluded. You know what's at the end of that central angle on a flat Earth? A mountain peak with an elevation just based off of the rise over run. So that is the difference in timing predictions and why it works out that way. And I have all of it labeled out here with screenshots from Stellarium showing the timing, starting with observer position at time of occlusion, so we know the positions there, and then going through all of it. We just rewind it 2 minutes 29 seconds, and then play it out from there. And as it continues on, you can read about how, you know, I break down the central angle relationship and the time components there. So you can read all about how that the exact time it takes to drop angularly 27 arc minutes is, you know, defined by the 15 degree per hour relationship set by the geocentric position of the star. And we went over the definitions of the geocentric coordinates and the celestial sphere last week on that. So there should be no issue there. But then anyway, after I show what it is for the observer, I do the same for the peak so we can see what it's like with respect to the peak. And then at that time of occlusion, it's at, where was it at? 243, 7. Yeah, with respect to the peak, it's at 233. So that's how that works out. And let me check my notes, make sure I don't have anything else to talk about. Oh, eclipses. Okay, so some people are saying it's a straw man to use the geometric intersection difference as a metric for correctness for predictions. Okay, because you know there's refraction in real life. I don't disagree that there is refraction, but we're interested in the cause of an occlusion, which is the geometric intersection of a source and object doing the occluding. So we're going to read off a couple of excerpts here. So this is from an astronomy textbook here, and this is about occlusions. So an eclipse is distinct from an occultation, which is the blocking of light. And then it gets into the shadow of the moon falling upon the earth is a solar eclipse, and the shadow of the earth falling upon the moon is a lunar eclipse. And by these definitions, the solar eclipse is really an occultation. So again, this is relating geometric intersections and the timing in which those occur, which is going to dictate the, you know, when you see the event. So he talks about the, you know, we introduced the Bessel function, or the Besselian elements and all that, the Besselian plane. So they get into all of this, and this is referencing the geocentric coordinates of the celestial body, which is the position is if you could view it with no refraction and see it exactly where it was at. And this is what they all reference everything off of. And so just more on that. So this is coordinates for the observer. This is what I mean by geocentric position. Consider an observer located on the surface of Earth at a longitude line lambda, at the geocentric latitude phi prime, at a distance rho from the center of the terrestrial spheroid, at the center of the terrestrial spheroid. So again, that's merging the celestial and terrestrial sphere models conceptually to make them work. And this is where the geocentric coordinates place that observer at the center of the sphere, and then the angular difference created by a radius of 69, or what was it? 3959 is what changes the star's position relative to that. So it's all based
Wait,
off of that. Go ahead.
wait, you just said it places the observer at the center of the Earth, but it literally says that the observer is at some distance from the center of the Earth.
Yeah,
So,
they're doing a transformation to the center of the spheroid to make it relatable. Like we just went over the transformations in the last one for the with the cell nav manual where the guy was talking about it. Like what I'm describing isn't wrong. This is how they do it. It's all relative to the fictitious observer at the center for the
I mean,
geocentric
it's relative
coordinates.
to him. Yeah, it's relative to him because that's the center of the coordinate system. But the observer observing the eclipse isn't assumed to be at the center of the Earth. He is assumed to be at the surface, so approximately the radius of the Earth away from the center.
Yeah, so they actually do a Besselian uh, plane transfer or whatever, and they end up doing exactly what I said by putting the observer at the center of the fundamental plane, which intersects the celestial equator, which comes out of the terrestrial equator. So all intersecting, putting the observer in the exact center of the celestial sphere to make the predictions. Like your way you're arguing isn't a real contention here. We're saying the same thing, and to use the coordinate system, you have to the geocentric coordinates. What they're referencing is exactly that. As we continue to read through these definitions, you're going to find that what I'm saying is an exact agreement with what I'm saying with these
Okay,
definitions.
but that implies the radius of the Earth is the factor necessary for predicting the eclipses, because if it was different, then the results will be different.
Oh, we have a radius of vision, and we're asserting that it's the same equivalence there. So if the
Oh,
Earth were actually geometrically a sphere, you would get different occlusion timings. So we're kind of being distracted from the geometric intersection point I'm trying to make here. So I'm going to continue
I mean,
now.
I can assert the Earth is equivalent in the shape to a dinosaur, and that assertion wouldn't really hold because you have to actually prove your assertions.
Yeah, and so we proved ours by the intersection difference in occlusion timings. So we're going to go ahead and swoop your coordinate system that's based off of using a radius value to do computations based on how the stars change at a linear rate at specific angles. So, and if that linear rate were true, and if those elevation angles were physically meaningful, then these occlusion timings would be the opposite. We would be off by the intersections would have occurred closer to the central angle here, or the half central angle, due to Earth curve, because the star is geometrically getting lower. So anyway, we're going to continue learning about the abstraction known as the fictitious observer using a radius value that could be the center of the Earth, or it could be the radius of your vision, transposed as a linear rate of which the stars would change at 60 nautical miles per degree. All right, assuming perfect uniformity. Anyway, the topocentric plane is the apparent or intermediate place where the location of the observer is on the surface of the Earth, not the geocenter. The topic-centric right ascension may be measured from the equinox or the CIO, and then the geometric place of the object is defined by the straight line between the center of the Earth or the observer and the object at any given time without any other corrections. So, lining up that geocentric uh, location with the geometric place of the object, straight line between the center of the Earth, and that goes on to show what they do with the Besselian transformation with the fundamental plane, using that direct intersection between the two, because you need a common z-axis to align it. What we looked at last week for the z-axis alignment, we pull up the unnamed. Oops, a second. Oops. All right. So they'll put the observer here, and then also the center of the celestial and terrestrial sphere will be here, and they do the transformation from here to here. But because this z-axis is aligned, that's what allows for that nice, smooth transformation there. All right. Let's see what else we got here. Reductions from the positions, from the, I think that's barycentric to the geocentric coordinate systems. So proper place. The proper place or virtual place represents the position of the planet or star as it would be seen from the center of the mass of Earth at some date. This coordinate system is defined by this acronym here for just establishing, geocentric coordinates, assuming that the Earth and the atmosphere were transparent and non-refracting. So again, using the true position intersection, not the apparent position of what we see, to make the predictions. And this is from the Supplemental Nautical Almanac, or the explanatory supplement to the Nautical Almanac and Ephemeris. So the geometric position is derived from the actual position at the time of observation. The apparent position in which the observer situated at an origin of coordinates would theoretically see the object. The astronomic position in which the corrections have been made for some small terms of aberration or whatever they need to adjust for in their tabulated catalog for the star positions. The apparent position is derived from the geometric position by the application of corrections for aberration where relevant for refraction. So again, this is how to how to adjust where, how to compensate for where the star is apparently versus where it should be with respect to their coordinate system using that 15 degree per hour deviation. So however, refraction is dependent on the observer's local reference system and is invariably treated as a correction rather than a blah, blah, blah. So it just goes into that a little bit. But again, exceptions only occur for this phenomenon that are essentially topic-centric, such as the rising and setting in principle, though the correction is neglected in practice for eclipses and occultations. For the geocentric coordinates, the apparent position of the is in the direction of the, for the geocentric coordinates, the apparent position is the direction in which the observer at the center of the Earth would see the object, and refraction does not enter. So astronomy is based upon geometric intersection timings, irrespective of refraction corrections. Those are added locally after the fact where the observer is going to be, and those will affect how the event is perceived and whatnot. I don't disagree with that, but the actual predictions start with geometric intersections as a fundamental principle, right? And then here's a diagram of what the Besselian coordinate system looks like with that fundamental plane and the observer intersecting here to make the predictions. Now, I'll be for realsies with you guys. This one doesn't make a whole lot of sense to me, but fundamental plane, observer here. That's the important part. Now here we have Fred Espenek from NASA. Or sorry, he's not from NASA. NASA cites him as as to the accuracy of their ability to make eclipse predictions. And this is all he gathered was different data sets from all over the world, from different times in history, from different civilizations that had their own charts for plotting out eclipses, because all you need to do is make the observation and then make another one, and then you could predict it out from there. Shane has a short video on it. It's pretty straightforward to make eclipse predictions. But so what he notes here is the geocentric ephemeris for the sun and moon, various parameters, constant, and the Besselian elements are given in the table of the elements of the eclipse. The eclipse elements are predictions and were derived from the DE200 and the LE200 in the Astronomical Almanac in 1984 and thereafter. Unless otherwise stated, all predictions are based on the center of mass positions for the sun and moon, with no corrections made for the center lunar limb profile or atmospheric refraction. So what he's saying here is that at this, like the sun has an angular size, sun and moon have an angular size of 0.5 degree. At the center of that 0.5 degree is what they're using. And then, not assuming any refraction corrections or anything like that. So using its geometric position to make their eclipse predictions. So this is what it's all based on, what it's always been based on.
That's not what center of mass means at all. A center of mass means the actual physical center of mass of the object, like inside of the object.
And would you represent that as one of these center points in one of these? Because that's all that's being referenced. That's exactly what it means. It means the exact center of the geometric position of it. There's no different from what I just said. You just corrected me by saying something slightly different and attributing mass to it as like a 3-dimensional sphere, completely irrelevant, not shown here. It's all done through circles and being at the center of the spheres.
This what you have here is the transformations that you make on the numbers in the ephemeris. So the tables that show you at what angle an object will be. But the ephemeris in the first place are derived from a model of the solar system where you have to include the physical positions and sizes of the object. So he's describing this previous step. How do you define, how do you derive ephemeris? What you have here is what you do with ephemeris after you already have them.
I see what you're saying.
Can you guys still hear me? Oh
I see.
yeah.
I see what you're saying. So the gravitational center of mass positions, so like the Berry center, right? Imbo?
Oh yeah, yeah,
Okay.
that's what I meant.
Right. Okay, yeah. And to get that though, you have to start with observations from Earth to get that, assuming the non-refracted positions to set everything up, and then you'll have your ability to predict, the gravitational position based off of those known true positions, not the other way around. It literally all started with this.
I mean, no, if you don't account for refraction and you want to measure distances to celestial objects, then you will get inconsistent results.
You're saying something
so that's just a
completely
completely
different?
baseless claim.
No. You're saying something completely different. We were talking about center of mass as as the point for the prediction versus the true position geometrically as defined by the 15 degree per hour relationship. And I'm saying that the center of mass position can only be derived after you have a true position for the, just the raw where the center of it is, using that 15 degree per hour relationship, the backbone of the whole thing. And then you responded by saying something completely different that were related to refraction, which we're talking center of mass. Like, so I don't know if you're not paying attention or if you're just saying different things and hoping that I'm not paying attention, but that needs to stop.
It's definitely that one.
You need to stay on point, because that's the second time you've done that tonight. And I'm not going to keep letting it happen. That's super annoying.
I mean, I said what I wanted to, so you can continue, I guess. Whatever.
Thanks. I will. So the backbone of all of this is based off of the geocentric positions. Without that, they have no ability to say, hey, we're going to use this reference frame for the center of mass. So the center of mass with respect to what? You need the geocentric position to establish it first. End of story. All right. So, are there any contentions about the geometric intersection being earlier on a globe? Does everyone understand what I was saying last week about this? Like, you can disagree as to why it occluded later saying refraction and whatnot, but geometrically, do you guys understand that if the Earth is a globe and Earth curvature is causing the change in the position of the stars, then as it's following the curvature of a central angle as defined by 2 points on that sphere, this angular relationship occurs for the star and the peak at an earlier time relative to the observer? Any objections?
I feel like nobody will agree with this. People just are too tired and think this is like too pointless to debate. That's why they don't have any contention, because it's just so.
Has that been the case the whole time when no valid contentions have been
no.
raised and people just doing dog shit tactics the whole time?
Actually, Embo, that's not the reason. The real reason is because you can go into Stellarium and verify the angular relationship and the time, which I've done meticulously and linked here. So the actual contention is that nobody actually has a contention. They just think that it should be later because of refraction. So saying that this is geometrically impossible, et cetera, is nonsense.
Like nobody's disputing that, like the geometric, as far as I can tell, the geometric thing, but we're disputing the geometric matters because you're using a visual observation, so it has to be the visual. Like,
well, everybody disagreed last week with exactly what he just said.
Yeah, first of all, everyone disagreed last week. And second of all, we're interested in the cause of the occlusion. That's why we referenced the geometric intersections. Now, the globe had a geometric intersection window that was passed. So we have to go to the mountain peak and check ours at the end of the central angle and see where the star's at. And if it's at the same angle, then that's a congruent triangle from star to peak, from peak to observer, which would only be possible if the Earth was flat and the star didn't actually angularly drop.
Well, it's not that there aren't any contentions, because as you said, there were many raised the last time. It's just that we know that you know those contentions, and I don't think this is worth repeating again, because
what's the
this
contention?
entire thing.
What's the contention then? Is it not geometrically, like, how is it you agree that this occurs, so there's no contention?
It's teleporting the observer to the peak, and like everyone in this Discord knows that you do that, but it was repeated so many times too, and you still ignore this. That like nobody does that anymore.
Yo, Embo, you're not gonna just come here and say a bunch of random shit. We go to the peak because the star traversed its central angle and got occluded. It has a chance to get occluded at 2 points during this central angle transit of 27 arc minutes. It has a chance at, let's see, 218, 4204. That's when it has a chance, and it has a chance when it lines up with the peak. And we check with the peak. If you have a problem with checking with the peak, that's your problem, dude. You
Maybe
can
I'm missing something. Why are there only two? Why are there only two? Yeah.
why are there only two? Because the star is flight source is only going to intersect with the globe at this time or at this time on a flat Earth.
Oh, one for globe, one for flat. Okay.
Yeah.
Isn't that
So
helpful seeing
so
seeing the alignment of all those three things that people kept confusing and muddying and switching between? How they're
so
all
la-
related distinctly?
so last week everyone was saying that this was geometrically impossible, it couldn't happen, yada yada. Now we can all see that this is what happens. This is what the globe predicts based on the observer, based on what they're saying the dropover distance is. All the math and angles and all those relationships are all on here. None of them are incorrect.
As far as I'm concerned, the globe predictions for the geometry, like ignoring refraction, aren't incorrect. They seem to be correct. But if you want to say that the globe will predict it sooner than flat Earth, then you not only have to compute the predictions for the globe, but also compare them to flat Earth. And the only thing you have here is a globe. Because if you were to show the same thing for a flat Earth, then all of the people who would see it's absurd. Last time you tried to do that, you had to teleport the observer to the center of the Earth for some reason.
Buddy, the
In fairness to him,
backbone,
that
hold
spreadsheet
on
does
one
calculate
second.
that.
Let me start with this immediately.
Sorry, yeah.
So the backbone of the globe is the geocentric transformation to the center of the globe. That's what we just read about. That's what all this stuff is. That's what all this geocentric coordinates is. This is what the beginning of this Umlin paper is. So if you have a problem with going to using a fictitious reference frame to explain that, that's one thing. And that's not even what was necessary to do in that diagram last week. We're already using the same coordinate system to show it. So what I'm showing you, what's shown here in Stellarium, starting at the top are all the observer positions at the relevant times at the observer location. And then down here are the ones for the peak. That's all that needs to be shown. It's not going to be a different thing. We're using the same conceptual model for the movement and testing the difference based on the time of occlusion.
You're not using the same thing because you're using the peak for the flat Earth, but you're using the observer for the globe. But the
That's
observer is the place where
that's what the globe predicts, though. You understand that?
and that
And using this intersection timing here for what the globe predicted, it didn't line up. This is your only shot for a congruent triangle on a globe. This one means the Earth is flat. This one means the Earth's a globe. This one means the Earth is flat. Do you understand?
okay. Let's just ignore refraction for a moment. Yes, this
Duh.
is what the globe would predict without refraction. But this still doesn't change the fact that the prediction for the flat Earth for the opposite thing is incorrect. Like
Negative.
saying
It's
that you got
Shane.
saying that you got the globe prediction right doesn't change the fact that you got the flat prediction wrong.
Dude, what are you even saying right now? We got the globe prediction right, but the flat Earth prediction wrong? Buddy, this means the
Yes.
Earth is a globe. This means the Earth is flat. It's that simple.
This
That's
is the first time
that's
I've
the
heard that the
intersect.
flat Earth
That's
prediction is wrong, though.
that's the intersection difference.
Is this
right
because we're
there.
wrong because we're right or whatever? Or what do you mean? How are we wrong?
Well,
So
if you
and
get-
also real quick, just to touch on the refraction thing, I don't care that you can add two different corrections, terrestrial and celestial refraction, to give the appearance to match our angle. We can raw dog it with rise over run to the peak every time, and we're closer every time with no corrections. And the reason for that is because this light source relative to the observer isn't physically dropping. And when it gets occluded, we go, hey, what was the star's reference at the end of this central angle here if we were to check? Oh, look, it's at 233. Interesting. That makes a congruent triangle. Shane, can you pull up the video of the congruent triangle diagram?
What?
One
Oh,
one
you
quick question
didn't
on
use
that
it?
point. Are you asserting that the globe needs congruent triangles?
I'm asserting that if the Earth were a globe, that this occlusion would have occurred earlier, and it would have created the only way for there to be a triangle where the occlusion time or the intersection time, I'm sorry, the intersection angle is equal to the mountain elevation for a globe. There's a specific time in which that would occur. Anything
It wouldn't
else?
be a congruent triangle because refraction bends things, so it isn't like a.
It's a geometric intersection, big dog. So even
Yeah,
if
no, I get that.
so even if it is refracted a little bit, it doesn't it would have to use up the entire amount of refraction as prescribed. We've been over that many times on here. And when you account for refraction, then the or astronomic refraction, then the star is 1 arc minute over the peak, which comes out to be seven real seconds. So it's geometrically over the peak by 1 arc minute at that time. So it should still be visible. And this continues on. Like that might seem like a small amount, the 1 arc minute, but when you go over different peaks, it varies to like 2 to 3 and sometimes 4 arc minutes. So the intersection difference there is inconsistent with what is asserted, because then you're just saying that it magically cuts off the refraction amount to be close to what the flat Earth predicts. And if that's
There's a question for you. Just look, I haven't had a chance, unfortunately, to go through the spreadsheet in detail, but why are there 2 globe prediction times on there?
2 globe prediction times. Let's see.
The row your
So
cursor's
yeah,
on.
yeah. So the first one is for the geometric intersections using true positions in the observer base position, and the second one is using the refracted position at the observer location. Because a lot of people were
Okay, so
saying that
with refraction, globe is more accurate than flat.
no, it would be
For
geometrically.
that
It
one, the
would.
time difference is 7 seconds versus 11.
It's geometrically over the peak. It still hasn't set into the peak yet, so it would take 7 more seconds. So now you're saying that instead of using all 12, almost 13 arc minutes of refraction, instead of using all of that, you're just going to use 11 of it.
Oh, but like the flat Earth number is off by 2 degrees, or sorry, 2 arc minutes, 1.29 arc seconds, or whatever. The globe one there with refraction is off by 1 arc minute, 12.9 arc seconds. So, like, substantially closer. About
It would
two-thirds the
so
number.
so listen though, if that hypothesis were true and the star were being geometrically lower, but it was refracting over the peak, then the true position of the star would have to get lower with respect to the peak to further compensate for that last 1 arc minute of refraction, so it would still be above the peak. And then
Okay,
also,
but
in addition to that, 1 second,
sure.
people want to use terrestrial refraction as well to raise the elevation of the peak, but there's no convergent light source there. Like that's not where the lines actually converge. It's just where they appear to converge. So what would actually happen if the refraction was lifting it up like that is the star would be visible inside of the top of the peak for like another 7 seconds, and that doesn't happen either. So I'm not
Yeah, but I
concerned
mean, like,
with after the fact corrections to say that the
my
position
point
was
is,
really
like,
here.
every experiment has experimental errors. Like, nothing is ever dead perfect in the real world. You're looking at
Yeah,
one model that's off by 11 seconds, one that's off by 7 seconds.
yeah, and we're closer every single time. And
Except for the one we're looking at right now.
literally every single time. You would still be geometrically over it with refraction.
But I mean, it's a 7 second error versus an 11 second error.
No,
It's
no,
closer to the globe.
buddy, buddy. It's not an error in that regard. This is the saying that the refraction is geometrically lifting it up over. So like if this were Earth curve instead of a mountain, as long as you could see the star, you would say that's how much refraction there was to lift it up. But because there's a mountain peak cutting it short, you're now just saying that, oh, it just matches and now it's measurement error. That's not measurement error. It has actual it's stated that it's mechanically lifted up geometrically over that peak still. So that's not a measurement error.
Yes.
That's literally the geometric prediction of the difference in intersections at that time, where it's going to take 7 more seconds to get lower, but it already got occluded. So
I
now
mean,
you're
using the
saying
same
that
argument for the flat, it should have been in the mountain for 11 seconds, but you can still see it. Like, the flat has the same problem. You're not holding it to the same standard.
We're holding it to the exact same standard, bro. We're talking geometric intersections. You're comparing our geometric intersection difference to an apparent position intersection difference when the true geometric position intersection with respect to the peak was 11 arc minutes off, totaling, they do that. That's a 1 minute difference, bro, in timing. 11
Okay,
seconds.
but remember, the globe
Uh,
doesn't predict you'll see the geometric. It predicts you'll see the refracted. So under globe theory, the difference between your observation and the globe theory refracted, as globe theory calls for, prediction is 7 seconds. The
yeah.
difference between flat geometric and flat, like flat geometric, which is what you're calling for, versus observed is 11 seconds. So what we're calling
Listen,
for is 7 seconds off. What you're calling for is 11 seconds off.
listen,
You're
and
not
I don't,
closer.
yeah, we are every time because we're doing raw, the
You're
geometric.
not that time.
Listen,
Not
listen,
the one we're looking at.
listen.
The one we're looking at is not
Hey, hey,
is
guy,
not the
are you gonna interrupt me as I'm replying to this guy to chime in? 1 second, Zanuck. So this is a raw geometric intersection. If we were to add corrections to ours as well for refraction, we would also make ours match. The point is to compare geometric intersections. And if you go off the apparent, right, you would actually be over and you would still have to wait 7 more seconds. If it took 7 more seconds for it to occlude, that would actually be decent globe evidence to support what you're saying right now. But it doesn't. In every single time, it's off.
And
It's
let me just
it's
get
always
down to this, 'cause I
geometrically
think
over.
this might illustrate your assertion in this whole process. Your whole argument here is that in your model of how the flat Earth should operate, we would see the geometric occlusion and not the refracted occlusion. Your
Nope,
model
that's
expects the
not
geometric.
it's not
Right.
my position at all. I'm saying using the geometric positions, we can predict the optical occlusion and the time at which the occlusion happens. That will form a congruent triangle from the observer to the mountain peak, and then from the mountain peak to the star with true positions using the intersections. We're not saying that you're going to see
So,
something differently.
so if we took your model and said, here is different mountain, we haven't measured it yet, give me your best prediction, the best you can do as to what the flat Earth predicts we would see as the occlusion time. Is that number using the same calculation method you'd use, or would you give that person a different number, like a different algorithm?
What?
Let's
To
say
compute,
I'm,
we
measuring Mount
we need the rise over run to the peak.
Yeah. But if
So we
I
need
was
the
saying, okay,
elevation
here's
and
the
a
setup, I'm
distance.
going to go measure it tonight for this hill, this data, this far away, this height, whatever, this star.
hmm
I give you all those numbers in advance. I say, predict for me what time it's going to occlude. Is that method on the green line using the same process you would give me if you were to
Yeah.
say this is
Yes.
my best
Yes.
guess?
Yes.
Okay.
Yes. And every time we're closer.
Oh, but the difference is the pink line isn't what I would give as our best guess. The white line, bluish white, whatever color that is, line is
Called it.
Yeah, but this
the one
isn't
I'd
the
give as our best
cause.
guess.
Listen, this isn't the cause of an occlusion, and this is cutting your refraction amount short to match our intersection. So like completely irrelevant if you want to use it. That's a completely different hypothesis. I just
I'm
included
just saying, if you
this
ask a
because you
glober to
guys,
give their best prediction with all the data given in advance, they would include refraction. They wouldn't ignore it.
and that doesn't cause the occlusion. So I'm not interested in that. And
That's the
also,
fundamental difference between our theory.
also being geometrically over it doesn't predict the occlusion. Like, so if we go
And again,
to,
that's the
so
globe
if
wouldn't
we,
expect it to.
hold on a second, dude. And then again, the globe wouldn't, dude, no, they invoke refraction 1-to-1 to lift up everything. And if they say that there's 23 arc minutes of refraction, then you need to use all 23 arc minutes. And when we do that here for this peak, now it's 2 arc minutes over, that's 30 seconds difference. So it should take 30 more seconds to set into that peak geometrically if it's being refracted over.
Sorry, what did you just
So
change? Because that just wildly.
I
Oh,
went to I just went to a different place because I told you
okay, yeah.
at different
So
places
yeah,
it's different amounts
that's
every
another
time.
example. So on
Minute
that one,
minute
the previous
30,
one you were showing, yeah. So
2
that one
minutes
just showed 12
40.
seconds off for globe, 27 for flat. That one 15 seconds off for globe, 41 seconds off for flat.
7 seconds off for flat Earth, 20
No,
seconds
I'm
off for
talking the
globe.
column Q, delta time on the intersection. The time difference is 15 seconds for globe, 41 for flat.
That's 15 seconds of real time that it would take before it sets into it.
Yeah. Yeah, the time error is 15 seconds in our model and 41 seconds in yours.
But the occlusion happened at this time.
Yeah.
When these when
Neither of them matches exactly, but the error is smaller for the globe model.
the globe model isn't
I'm using
predicting
your
the
spreadsheet.
cause
I'm
of
not
the
even
occlusion.
controlling it.
Dude, I know, but this isn't the cause of the occlusion. We're doing raw geometric intersection differences. You guys are 2 minutes off.
That is the fundamental difference between our theories. Is in your model it's a raw geometric, and in our model it's not. That's a big difference.
Buddy. If
Halfway
we apply
through,
it,
everyone
listen,
switched.
listen, buddy. If we applied a correction to ours, it would just match. It would be the same.
You said that was why
This
I asked.
the,
If I gave you a number, would you use that same algorithm, or would you use a different
yes,
one?
yes,
So that's
because
your best algorithm. That's the closest. So
Show us
because
a formula.
buddy, the object
not
of
correct.
the hold on a second here. The object here isn't to compare or after the fact corrections and see what we can do to make it match. It's comparing the geometric alignments. This is the purpose of it. What you're
The
doing,
actual observation was the time.
yes,
And
the
our
time
model
that
predicts
it,
the time
and the
quickly.
time of that occlusion, we were 7 arc minutes in angular difference from our prediction, and you guys were 20 arc minutes from angular
But
position.
the pink one is not what the globe calls for. The globe calls for the white line, not the pink line.
Sorry, dude. Are you making a geometric occlusion prediction off of the true positions?
No, I'm making an optical occlusion prediction. The thing you're actually measuring is optical, not geometric.
Okay. Well, you predicted the wrong time then, because you actually need to add 15 seconds to this occlusion
I
time
agree.
that
We're
occurred
15
here.
seconds off. The model is not perfect. Your model is 41 seconds off. Our error is smaller.
Listen,
Not perfect, but it's smaller.
listen. You don't get to mechanistically cut your refraction off and then say, oh, my after the fact correction also happens to match the flat earth, dude. That's preposterous.
I literally have not touched this spreadsheet. I am looking at your calculations of our model.
I know.
Your calculations say our model has about a third the error of yours.
You're misinterpreting the data, sir.
Listen, if your hypothesis of this amount of refraction were true, then it would take 15 more seconds to set. So it's not valid. If it did take 15,
41 seconds off.
if it did,
You're over talking him. Can you steel man his position?
Alan's?
No, he's talking about refraction. Of course not.
Yeah,
So
can you steel man
Alan's
Alan's
or
position?
mine?
Can you steel man Alan's position?
Basically, my understanding of Alan's position is that by using the mountain peak, you are effectively able to ignore refraction. You can look at the occlusion time, and that gets you a pure geometric result rather than a refractive result. I disagree with him on this, but that is what he seems to be arguing. And because of that, you should be using pure geometric calculations. But
Well,
I think that may well be how it works in his flat Earth model, but it is not how it works in the globe model. So I think he's incorrect in using the pink row to represent the globe, and he should be using the white row instead.
Well, he explained why he's doing that, and you talk through him like mid explanation. So it's kind of like you're not listening to him. You're not trying to understand. That's how it's coming off.
Yeah. So
I'll shut up for a minute if you'd like. That's fine.
Fantastic. So to predict occultations or eclipses, etc., everything that we went through is based on geometric intersections of source and the occluding body. That is what we're doing in our comparison here. We're not saying that if you apply a second after the fact correction or what have you and chop off the exact amount to make the occlusion timing match perfectly, that it doesn't that it wouldn't be closer. That's retarded. At the time of occlusion, Flat Earth predicted this angle here. This was the angle of occlusion, or when it got occluded. This is the angular difference. This is what the globe predicted. This is the angular difference, right? The cause of what we see was predicted by flat Earth geometry. The fact that you could say that it works on a globe and what the globe predicts by chopping off your own refraction amount, that is exactly compensating for this central angle drop here, like by twice as much almost. You don't get to just chop it off and say, hey, oh, look, it matches we're only 15 seconds off the occlusion time. No, you would have a completely different occlusion time. There's only one occlusion time, and it's based off of geometric intersections. We're closer every single time. That's all it is. It's that simple.
Didn't we all
So-
just agree the importance of the backbone of the globe model is the geometric intersection of the points and how it all works? And everyone was silent, no one disagreed, and now we're right back to, well, no, you can't do that.
Well, I may not have been here for that one or something, but yeah. So, okay. Yeah, like I guess you're using your model of this measures geometric intersections to judge the globe theory, which does not say that an optical measurement is geometric. That I think is your fundamental error here.
An occlusion is
What?
geometric, dude. Once we no longer see the star, we just need to know what time it was, and we can reference with accuracy of the globe model to determine the angle of the star to that observer and also to the end of that central angle, which happens to be where the mountain peak is. That's all we're doing.
I've registered my objection. I don't think I've got much more value to add, so I'll let you continue in any other direction you care to go. But that's
Thank you. Much appreciated.
I hadn't realized that before. It's just kind of funny to me.
No problem. So, again, the importance of the backbone of all of this is geometric intersections. And you could find this endlessly in different textbooks. I just took some excerpts out here, but I got a whole section on it here in, let's see, notes, astrorefraction. I think there's some in here where they talk about it all. So all the references can be found there regarding the geometric intersections, the cause of what is being seen. So the star's true position started at 233 for the observer, and it got occluded at an angle that makes a congruent triangle from star to peak to observer at 231. Oh, sorry, that's actually too far. My bad. At 233, sorry. So at the end of that central angle transit is when it got occluded. Now, whatever this air difference is here, could be refraction, could be how the coordinate system doesn't overlay with reality properly or whatever. But in any case, this central angle, or like this difference here, so 27 plus, 7 minus 20 here for this globe's geometric intersection is 13. And that always comes out to be what their central angle is, what they would predict as globe drop. So the prediction within any arc length on the so-called globe, we can predict the geometric intersection that will cause a star to be occluded more accurately than the globe can, using the geometric intersections. Using the apparent positions, their amount of astronomical refraction prescribed to them puts them geometrically over the star, meaning that the time of occlusion should occur later. But it occurred when the geometric intersection was close to the flat Earth prediction, because that's the end of the central angle. That's as much time, that's as much as you get. If refraction were mechanistically viably lifting things over a curve like that, then it would have to exceed that central angle. They would have to exceed that 50.5 kilometers to get lower for the observer to actually make that match for what the globe predicts. An occlusion 7 seconds later would be good evidence that that refraction works the way that they say it does.
When you're saying that refraction didn't fix it all the way, are you trying to say that it isn't perfectly predicted to be 0 seconds off, that it's 7 seconds off still? Is this what you mean? Or do you mean something else?
I mean that if you say that there's a specific value of refraction attributed to why the star is at a specific angular position, then that full amount of refraction has to be used up for a geometric intersection before it would be occluded. If you use anything less than that, then you're cutting that amount short just to match the occlusion timing.
I'm confused where geometry comes in play to this, because refraction is an optical phenomenon, But if you want to say, if this is what you wanted to say, that you have to use the entire value of refraction that you predict for a given time, then yes, I do agree with this. You can't just cut it, like use less or more than the amount you predict. You have to use the entire amount. If this is what you meant, then I agree with this. But maybe you meant something else. I don't know. You can maybe clarify.
Well, I've been over it several times with you, so I want you to write this one down so that I don't have to repeat it. Are you ready?
I mean, this will be saved, right? As a presentation on YouTube, so I don't have to.
Yeah, you say
Yeah,
that.
you don't have to
but
listen
this
or
is
look at
but this
stuff. It's
but this
Embo.
is but this is going to be the third or fourth time now. So I just want to make sure that you specifically have the answer to it. So you have a pen and paper ready.
Yeah, I actually have.
Fantastic. All right. What was your question again? It was,
What my question was, when you said that you have
yes.
to use the
Yes, it was about the
Okay.
amount of refraction. Yes. So
Yeah.
if they're saying that there's 12 arc minutes of refraction, then the star should be at like 203 instead of 206 relative to the observer, because it has to get down that last arc minute and 12 arc seconds of refraction. Although I wouldn't even count the arc seconds, so it would just, the arc minute is the important one. 12 arc seconds isn't a lot. But in any case, it has to use that full amount. It can't be just cut off arbitrarily to match, just to say like, oh, it just, well, it wasn't this much. It was actually 4 less, it has to be the equal amount lower than the object occluding it. Because for every instance where there's an observation like, Mount Canigou or anywhere, or like the Novaya Zemlya effect, they say that, whatever amount of refraction is needed to explain it, that's how much was there. So that's a 1-to-1 relationship. So to say that there's 12 arc minutes of refraction here, then the star would have to be, its true position would have to be 12 arc minutes below the peak. Well, this is almost 13 because it's 1242. That's pretty close to 13. So, but anyway, it would have to be around that range, not a full arc minute lower, because that's 7 seconds of transit time. So it's above it still.
Oh, I now I get what I mean. Yeah, that's it would have to basically be that amount of refraction lower than the peak, because the peak is the moment of intersection. So this difference, it boils down to the fact that for the peak, use the geometric location of the peak, but the peak is also refracted by its own amount. Basically, it's just
great.
this.
Yeah, great, dude. I'm so glad that you agree with the geometric intersection part. Now we can focus on the apparent position. So I have down here added the terrestrial refraction. It is geometric globe plus standard refraction. Now I do have these, but the reason that I don't consider them and will not consider them at all is because an apparent image is a virtual image. That's where light rays appear to converge. There's no actual light rays converging there. They will never cause interference with light rays that are interacting with them, because there's nothing there. So the apparent, altitude of the mountain that is increased by 2 arc minutes for terrestrial refraction plays no role in the occlusion or the like in that mechanistically. And like I was talking about earlier, if there was a 2 arc minute apparent image of the mountain, then the star would set into that apparent image because there's nothing to occlude it. So you would have a star inside of the mountain at the time of occlusion, and you would still have to have the geometric intersection threshold crossed. That's why I include the geometric intersection threshold for the astronomic refraction position, because I'm willing to entertain the astronomic refraction bit, but the occlusion has to be physical. So I use the geometric intersection point for that.
Yeah, the cause of the occlusion is physical, but we were talking about the location at which we see the occlusion. In order to convert the angle to the time, you use the angle as the reference, and the angle is optical. So it is so
Well, but no one's
even though
measuring
you
an angle here. All we're looking at is a star being occluded and referencing true positions. So all we've
yeah,
done,
but then
rise over, run to the peak, is just what the math is for that. Like that's like no one measured that with a thing. Like if you got a theodolite out, that would measure like 219 or something like that, 218, 219. We're not saying that the optical angle wouldn't be that. We don't care about the optical angle. We care about the geometric intersections because that's what causes the occlusion.
yeah, but it causing the occlusion isn't the same thing as you observing the occlusion in its geometric place.
Yeah, and
Well, one
that's
doesn't
not
logically follow from another. Like I don't know.
correct, and that's why our spreadsheet compares geometric intersections and not apparent positions. I just included this for you guys because you guys like to say, all these claims about how we don't account for refraction, etc. We do explicitly, but no, I agree, and that's why the spreadsheet is divided up into two sections here for the intersection difference for what flat Earth predicts versus what globe predicts for the geometric. The apparent could be whatever the fuck we want it to be with after the fact corrections and saying the star is here and there. That doesn't matter. We're doing raw geometric intersections.
I mean, it really cannot be whatever you want. I heavily disagree with that, but okay, like
Sure,
I already told you everything I wanted to, and that was kind of my point, that like all of the objections that you could have, that you can make, were already told to you. So
yeah.
it's
Well,
really just pointless to repeat ourselves.
It is especially pointless to repeat yourselves, and here's why. Because we open up most of our presentations here with this, because you guys like to say that about the refraction position, increasing the elevation. And you guys to date have never provided a single demonstration of a virtual image occluding light. Ever. You guys never do it. So it's really weird that you show up with the same physical talking point, but no actual demonstration of a virtual image occluding light.
Nobody's saying a virtual image occludes light. It's a physical mountain. It's just the question is where the light is and where the mountain is when the occlusion happens.
Buddy, they're actually, like, I don't know if you're like haven't been paying attention, but they're saying that the mountain has 2 arc minutes of elevation added to it geometrically. So 217 plus 2 arc minutes of actual physical elevation to cause an occlusion because it would be refracted up by 2 arc minutes. The refracted amount that's being added onto the 217 is an apparent image. It can't occlude light.
Okay, you don't understand.
No.
Yeah.
I understand it very well. We have a mountain peak that's at 217, and we have an apparent image that's being added onto it that's 2 minutes of terrestrial refraction. So the mountain peak appears to be at 219, 218, something around there. But that 2 arc minutes that's being added to it isn't physical. You wouldn't say that the physical angle to the mountain is 219. It's categorized specifically as a different thing. And on top of that, an apparent image is a virtual image. Virtual images don't have light rays that converge from them. It's an apparent thing. It looks like that. So there's nothing actually there to interfere with rays that are coming in from behind it. So if you have a star setting from above it into an apparent image that you're looking at, there's nothing that it's interacting with physically. So you're going to see it go through it. And I actually have a demonstration of that I show right here. So I'm looking through a window. It's at nighttime. You can see the reflection of the hallway in the window. There's a light source outside here. I'm going to try and use the apparent beam to block the light. It doesn't happen. Let's take a look. All right, a quick lesson on the principles of the cell Theo. So what we're looking at here is you can see the pattern of that light is distinctly different from the lights that are in this hallway here that are being reflected out into the mirrors or windows there. But what you'll notice here is that the reflected beams, so like this right here, gets reflected out into the images, and as we move over, we can see that when we intersect the reflected image, it doesn't block the light. The direct light source is right there, doesn't get affected when we move into the reflected images, right? The only thing that actually blocks that light is the physical object, and we must overcome that to see the light again. Okay, so what we're looking at here as we move, you see. All So an apparent image has no bearing on this analysis at all. That's my position.
It's actually quite funny. I mean, this is not really analogous because it's reflection, not refraction entirely, but it's still a little bit funny that even in that apparent image, like other parts of this apparent image are obstructed by other parts of this apparent image that are like closer than the further run, like ones like like the frames of this window that are in this apparent image, they are blocking the apparent windows that seem to be behind it. Like they aren't actually behind it, but you know that apparent image that depicts something that's behind.
It's reflecting this outward from my perspective.
Yeah, but like different parts of this apparent image, they seem to be obstructing one another. The ones that depict the closer object seems to be obstructing the ones that depict the further objects.
Did you happen to see that light source get occluded by the apparent beam? Yes or no?
Light source gets.
Yeah.
What? What is this supposed to be an analogy to?
Dude, a virtual image, right? Reflected or refracted is a virtual image. It's an apparent image where light rays appear to converge from, but they don't actually. So this is analogous in the sense that a virtual image has non-convergent light rays. And what we have here is a street light outside, and it's not occluding the beam here, which is a reflected image, which this is a virtual image. Light rays appear to converge from here, but they in fact do not. The light rays coming from the street lamp outside are not interacting with anything here because there's nothing there to actually interfere with it.
It's because it's in front of the pillar.
It's in front of the pillar. It's a virtual image. That's why. Now it's in the
It's in front of the pillar.
Buddy, the pillar is right next to me. This right here. Right here. The pillar is right next to me. You're looking at an image reflected into the window. Here. The light source is outside. This is a series of reflected images. So anyway, the light source not occluded by virtual images because no light rays converge there. If anyone has a demonstration of an apparent image occluding a light source, that would be super welcome. And we've all seen this one as well, where the light source shows up in the apparent knife because the apparent knife doesn't cause an occlusion.
Let's stop there for a second. Can we stop there for a second, Alan?
Yeah, where?
Go back to that. God, why did I
Sorry, this one?
lost it? Yeah, I just clicked on the wrong thing here. How to get back to your thing? Jesus Christ. Discord. Clicked on the wrong button.
Why are you trying to find it? So, Alan, you're looking like right in front of you, just in front of your hand there is a window or a mirror.
So
is that right?
Not that one. The one
Yes,
with
it's a window.
knife through the water, cup of water.
Hang on 1 second, Zanuck. Let me get through Roundhound real quick.
Using it as an example. We saw that before.
Yes.
Yeah, there we go. So you're showing that we're looking at something that is being refracted through one layer of glass and water. And you're comparing it with something that's going through 2 layers of glass and the water behind the knife.
Yes, we are comparing a virtual image that is inside of the glass to the real knife that is also inside of the glass. And when the light source is intersecting with the apparent image, you can see the light inside of the knife. And when the light crosses the actual knife, it's no longer visible.
And where's the light source coming from?
Taylor's hand. She's holding a laser and she's moving it back.
Is the knife
the light in the room? Is that what you meant?
Guys,
no.
Guys.
Is the laser going through 2 layers of glass while the knife is going through 1 layer of glass? Yes or no?
It's only going through 1 layer of glass.
So would that affect the position of that light? Why would the refracted image of the knife not be affected by not affect the light beam? Because the light beam is actually being refracted twice.
Because no light rays converge from the apparent knife. They appear to converge from it. There's nothing there to physically interfere with them. You're overthinking the situation with the glass and all that. All this is if there's an apparent image, the light source will not be occluded by it. That's it. Just you can think of any example you want. It doesn't occlude it.
But the laser isn't the light that's causing the refraction. The room, the ambient light in the room is what's causing the refraction.
No,
Buddy,
the light,
That
the,
doesn't sound
buddy,
like
it's a
the
it's a
glass
laser
is causing the
pointer.
refraction.
It's like
The
yeah.
glass is causing the refraction.
I know the glass is causing the refraction. Sorry, but we see it. We see it because of the light in the room. The laser is a different light source. I
Listen.
don't think it's a valid observation, to be honest.
listen. Great. Can you do me a favor and show me a virtual image including a light source? If mine aren't good enough,
Yeah.
guys, just show
Yeah,
me a virtual image including a light source. Go ahead.
all you gotta do is look at that the propane dropped on that container that blocks a red light that's below it, and when you drop the very
Oh.
cold,
Oh, I got you.
right? That is your why is the laser now rising up and now not being occluded, whereas before it was occluded because it looms up due to the variance in density and the angle of incidence.
All right.
Go back a little bit.
Yeah. 1 second. Zanuck, I need you specifically to watch this in its entirety when you get a chance. It's a really fantastic video on refraction and this exactly. But yeah, we're going to show you here exactly what's going on. So there's a difference between a geometric occlusion, like something being actually blocked, versus like an optical occlusion. So in the example for the propane tank here, where is it? Give me 1 second, trying to find it. Is it? It's not that one. Bear with me, lads.
What exactly is the contention? They think that virtual objects block light now? Is that
yeah?
No, the light path,
no. 1
path of
second.
the light is changing due to refraction. That's what
1 second.
that's what's in contention.
1 second. No one's
it
contending.
didn't answer my question.
Yeah, no one's contending that light can, be bent and change directions and shit when you introduce a different medium and all that. But what he said specifically was that there's a geometric occlusion here, and that when a different medium is added, the light ray goes over it. So why isn't it blocked? Now, what he referenced wasn't even analogous to what's being discussed, but we're going to go ahead and break it down anyway. So in this example with the propane tank, what we have here is this can with some Play-Doh on it. This red Play-Doh and this blue Play-Doh are geometrically above. When you watch the video, they're geometrically above this container here. And this camera has been lowered so that it just happens to align optically with the container and the red Play-Doh. But keep in mind that behind that object, and it's not even attached to it at an angle, mind you, it's fucking just behind it, but higher in elevation than it, right? When he adds the second medium, let me see if I can play it out from here. When he adds the second medium here, the light rays get bent up a little bit and you could see it, but there's no geometric occlusion here. Now, what Vanby did, and here's the timestamp for this specifically, guys. Highly recommend you guys watch this. So
Wait,
what
is
he
there a
does,
geometric conclusion of the red Play-Doh right now before you start the video?
optical.
Would you agree there's not a geometric occlusion right now?
It's optically occluded. The
Why
red
would you say
thing, because the red, I'm going to show you the distinction here in a second. Let me continue. So the elevation of that red, it's actually physically over the tank, but for the observer on the other side, it's optically being blocked at this side. So there are light rays that are coming out over extending that aren't visible because it's being optically obstructed from this. But this isn't geometrically lower than it. Now, well, hold on. Just Zanuck, for the love of God, just let me.
I'm not saying anything.
No, that was me. Sorry.
Oh, I'm sorry. I could hear you starting to cue it up. It was Roundhouse. Just settle down for a second, because this is extremely important, guys. You have to.
I'm totally settled.
You have to follow this. Thank you, Zanuck. I appreciate that. I apologize. I thought it was you. So when he adds the liquid there, the red Play-Doh does appear, and I'll see if I can. Yeah, there we go. Perfect frame. So there it is. Now keep in mind, its elevation is physically higher than this tank, and that's going to be extremely significant when Vanby does a follow-up demonstration here. So this is a side diagram of what it looks like here. The occlusion here It's being optically blocked, but relative to this, it's still geometrically above it. So what Vamby does in his rendition of it, oops, 1 second. Okay. So he has the object doing the occluding, and it's geometrically higher than the light source he's trying to refract up. Here's our observer elevation. Here's the setup. And when he adds the medium, nothing happens. It doesn't geometrically lift back over it. So there's a big difference in what's being talked about there. Now, secondly, Zanuck, what was being discussed specifically, and why this isn't even analogous, but I humored it anyway because my boy Vamby just absolutely crushed this. Why this isn't analogous here is that they're saying that this container is actually lifted up a little bit and it's blocking it because of a virtual image. Putting a medium on top of that behind it and then having the light rays bend is nothing to do with what we're talking about. We're talking about light rays not appearing to converge from a source, but they're not actually doing it because it's a virtual image. It's an apparent image. So it has no power of occlusion because it can't interact with the actual light rays. That's all it is. This is not analogous at all.
It's not a virtual image. It's anything that you see, the light has had to travel from it to your eye. So as far as your eye is concerned, that is where the physical object is, and the light that's being occluded by it has to travel the same path to get to you.
Negative, Ghost Rider.
Has anyone ever seen a star through a mountain?
Exactly. That's exactly my point. They're saying that the mountain is being lifted up virtually by 2 arc minutes, by an apparent image. It appears to be a little higher by 2 arc minutes. There's nothing that converges at that 2 arc minutes that's being lifted up. It's apparent. Hold on a second.
The light of the star.
It's real important to understand this.
Has to travel the same path that the mountain does.
Oh, when I said that, you figured that just meant finish your thing really quickly? No. So what it meant is follow this through. This is not the same this is not analogous to what's being put forward here. So this is a different scenario entirely, where this is elevated above the thing, optically occluding it, adding the medium, bends the light ray that's already geometrically over it. But for the observer, that's what makes the connection there to lift it. What's being said about an apparent image causing an occlusion would be if this container was refracted and was being lifted up, and then an object was being lowered like a light source, and that light source got blocked while it was intersected with the apparent image of the container, not this image at all. You guys are conflating separate things here. We need to stay on task for the occlusions.
Well, then you'd have to.
You keep saying it's high though. Like just putting the camera down and putting the cam with the Play-Doh on it higher. This doesn't mean it's above the tank. Okay,
Yeah,
you just roll your image to the right slightly, and they're both level, and slightly under the tank. You can't say it's above the tank.
Yeah, it's below the tank. The red is below the tank starting out. Hold on. Let me just
It's physically over the tank,
It's obvious
guys.
to me. I'll let you talk for the whole time. Let me just say my point. So go back to the tank. You keep on saying things, and just saying it doesn't mean them true. The red area is below the tank. In your line of sight, it is blocking, it is obscuring the red area. It only becomes apparent when you pour liquid propane on the structure, which makes that medium much more denser near the surface, which in front of it and behind it, which bends the light down toward the denser medium, which obviously now looms up the red area, Play-Doh, because the light is bent just one area. It's not like the differential form of Snell's laws we talk about under the globe circumstances, where over a long distance, over the curvature of this curved medium, we have light continuously being bent downward, in almost infinitely small segments. We're talking about this one. Yeah, that red thing is below the level. When there's nothing's being poured on.
How do you know it's below?
Yeah, Zanuck. It's not. They don't show it. It's literally in the video, and you could see that it's.
So why don't you see it then?
That is literally over it.
It's optically obstructed.
Vamby,
it's not geometrically obstructed.
Or not Vamby, sorry.
How do you?
Zanuck,
How can you possibly say that?
Zanuck, because it's only optically obstructed relative to the observer being lower than the thing. This is geometrically over the object occluding it, right? That's what we're
Roll
saying.
that image a little bit to the
shut,
right.
yo, I'm about to roll your volume all the way down to the left so I can finish talking. So what happens here is that the light is coming over, it's already being emitted out everywhere over top of this, right? It's already geometrically exceeding it. When you add the medium, it lifts it up, showing the virtual image of it. I'm not saying that's not possible. Shut up, please. I'm not saying that that's not possible. What I'm saying is that that's not causing a fucking occlusion. That's what we're talking about right now is not even analogous to the occlusion. We're actually off topic now.
No, we're talking about basic refraction.
No. I mean, listen, no, you actually, no, you actually can't. So listen, what they're saying with the mountain being an apparent image would be the same like as saying that this barrel, right, is actually a little bigger because it's an apparent image of the barrel. So they're saying that the apparent image causes an occlusion, and I'm saying apparent images are virtual images, and that virtual images are where light rays appear to converge. They do not actually interfere with anything. They do not cause an occlusion. This is occluded because the observer here is geometrically under this object, but the thing that's about to be refracted over it isn't geometrically under the object either. That's why Vanby did the experiment where he measured it out and made sure it was, under it and to see what would happen and whatnot. And it doesn't lift it up analogously. Now, real quick, stick to the actual point, because this is the only thing I actually care about. I could give a fuck about this, really. What I actually care about is that you guys are saying that this barrel would be like an apparent barrel, and it's actually higher in altitude, and it's causing light rays to be occluded from it. But we see from the apparent image here doesn't occlude light rays. We see the apparent image in this mirror doesn't occlude light rays. Apparent images are virtual images where light rays appear to converge. I'm almost done, Zanuck. I know. But you hear me out.
Well, you're going on different topics.
No, you went to a different topic completely. I answered it thoroughly, showed you the differences, and now I'm trying to bring us back to the original point of the occlusions, which is right here. An apparent image never blocks the light source. Go ahead.
Okay, thanks. Go back to the barrel again. I mean, this is a very key point there. You're just missing the point that, yes, if that red area is not being seen, it is not being blocked optically because there's no refraction going on between that camera or the eye and that object. Now, if you wanted to really do this test properly and really make it more analogous to your contention, what I would do is do this test again, but have something behind the green and the red Play-Doh, behind it, to the right of it. Maybe a laser, having it shining to the camera, and see if it then looms up and blocks the laser. And then that would then show our point, which shows that things that are loomed images, which are still real images, your eye is only following the light emitted from those objects. And if light emitted from the objects has a curved path, then they will be loomed up or down, depending on whether the refraction bends the light down or upward. So my point is, if you really want to do that test properly, put something behind the clay thing, or do an experiment where something's behind it. You're going back to your knife one again. That is complete conflation of all the ideas of refraction, because you have a laser behind going through a layer of glass, then being refracted, then coming out of another layer of glass, which shows that the knife will not block that refracted light source, because the knife's only going through one layer of glass with respect to your eye. So it's a completely erroneous test. It doesn't really show anything other than the fact that you have more refraction going through two layers of glass than one layer of glass.
I'm going to make this really simple.
Zanuck, I'm going to make it even more simpler, Aldous. The apparent knife never blocks the light source under any circumstances ever.
You can't say that because you can put the laser inside the water and it won't block it. Yes.
Oh, buddy. It only blocks it when it's geometrically intersected. And if you put it in, then it would be already bent. So when it geometrically crosses, it's not going to interact with it that way. But the purpose of this, right? This is a separate thing that you're conflating the two, right? This is a mountain peak that they're saying. Let me just use this. So they're saying this green circle here right? They're saying that it's not 3.5 inches. It's actually 5 inches because it's an apparent image, right? So if you were lower,
yes, the light between the camera
no,
and the ball.
listen, no,
I'm listening.
that's not what's happening. They're saying that this itself is refracted, not what's
Yes.
behind it. So pay attention. That this
Both.
stop. That this is refracted up. Okay.
Mhm.
Now, when a light source is getting lower and lower and lower, when it interacts with the apparent image, it doesn't cause an occlusion for the observer because there are no light rays that actually converge at that image. It's an apparent image. So when we look at the glass, it doesn't matter how many glasses or waters. The main point is that there's an apparent image in this glass, and it doesn't occlude the light until there's a physical intersection. And the same thing happens with the virtual image projected into this mirror. It doesn't matter the scenario. An apparent image is an apparent image. An apparent image means that there are no light rays that converge from it. Do you agree or disagree?
Man, there's a lot of confusion going. You can look
Do
at
light rays converge from an apparent image, or do they appear to?
Yeah, I know. I don't understand what the
Do
word
they?
converge.
Oh, you two guys are ridiculous.
Do they
It doesn't make any sense what
converge?
you're saying.
Listen, go to
It
Wikipedia.
does make sense. It does make sense. It does make sense. Yo, real quick. Yo, guy that said you didn't understand it, real quick. So on the Imperial Japanese flag, you have a red dot in the middle and you have a bunch of lines converging on the red dot. That's how light works with a source. The light converges onto the source in which it came from, the path of light. That's what's being spoken. It's not that complicated. Stop wasting everyone's time.
Thank you.
Yeah,
It's literally
the last 10 minutes.
no, stop. Stop.
If you look at the barrel experiment for a second.
Aldous.
One-
I got a better one. Is a virtual image where light rays?
You guys are dominating.
I don't care.
That's not your presentation.
Listen, guys. Listen, it's not a democracy here. So Aldous, simple question. Is a virtual and or apparent image a place where light rays appear to converge from? Or do they actually converge there? Go ahead. Yes or no? It literally can't get any simpler.
This is very alien to me, but I'm pretty sure they would still, like if that's where the light's coming from, it reaching your eye, that's where the light's coming from to reach your eye.
Incorrect.
You can't tell what path it took to get to your eye. You can only tell what direction it's coming.
It's not about telling which one. It's about physical intersections. If they appear to converge there, then like you'll see it like it appears to.
Intersections and appear together. Those are different things.
Oh my god, dude. Buddy, that's our fucking premise. That's what we started with.
Jump between physical and apparent and treat them.
Oh my, Aldous. No one's jumping between physical and apparent. That's literally you guys' position saying that apparent positions occlude objects. A virtual image. Real images are those where light rays converge, whereas virtual images are locations from where light appears to have converged. So, simple question. Is an apparent and or virtual image a place where light rays converge? Go ahead.
And you say it appears to converge.
That's because that's what makes the apparent position. That's what makes it apparent.
Yeah, but that's all you can measure.
That doesn't listen. It doesn't listen,
That's all
guy.
you can measure.
Guy. It doesn't matter.
The oil rigs block Catalina.
Listen, guy. Asking something
When
completely separate, Zanuck. Try and stay focused here, man. So listen, Aldous. A virtual image can't cause an occlusion though, because there's no rays that actually converge there. So there's going to be no interference.
So is your argument then that occlusions must be geometric? Are you saying that occlusions
100%. That's
Okay.
30 weeks
This is
in,
where I was
yes.
going with that barrel experiment. If in that barrel experiment, the camera doesn't move, the objects don't move. 1 minute it's occluded, 1 minute it's not occluded. Nothing physically moved. So either they were, I don't even know which it was. It may have been that they were geometrically not occluded the whole time. Maybe they were geometrically occluded the whole time, but the refraction changed it. It went from one to the other. So it cannot be purely geometric because the geometry didn't change, but the
Buddy.
image changed.
Okay.
Occlusion changed without the geometry changing, so occlusions can't be purely geometric.
Here's why here's where you're confused and wrong, right? This barrel is the geometric thing blocking, right? Lifting a light ray from behind the object is not in contention. That's an effect that we all just witnessed and saw, right?
Okay.
We're saying that this barrel, if you were to add some height to it for apparent size, like if there was some refraction here that was actually lifting the barrel up to make it appear to be a bigger size, that wouldn't, and if you were to like lower a laser behind it, that the laser would not be occluded in the virtual image because that's where light rays appear to converge. Lifting light rays, please do not make another unanalogous scenario again. I can't do it again. So adding a medium to this is not, and lifting it up is not what's in contention here. And on top of that, the occlusion actually is geometric because when the elevation of this object that's behind this object is actually lower than the object occluding it, then you can never get it to lift up. That's what Van Bee's whole presentation and experiments were done, or what his measurements were all done on. So it doesn't even work that way, where this is lower and we pour this on it. No, it doesn't. Bro, go watch the fucking video. It's literally higher than the barrel. You guys are all saying that it's lower. You guys are all sadly mistaken. Van Bee, are you here? Van Bee, are you here? Can you? No, it matters specifically because when it's lower, it doesn't actually lift up because it's geometrically occluded. Occlusions are geometric. Ta-da! But anyway, a virtual image of that barrel wouldn't occlude anything. That's it. Okay, lifting an object over it with refraction isn't the barrel occluding it, guy. That the light rays are appearing to okay, dude, that's actually perfect. Okay, Aldous. The light rays in the barrel scenario, when they get lifted up here, right? They're appearing to converge here, but we know when there's no medium forced on between here that the light rays don't converge from there and there is no apparent image there. If you were to introduce a laser or something to this red thing, it wouldn't be occluded by the red because it's an apparent image. Okay? The physical barrel here is what's occluding.
I agree with you. Good test. Yeah, I don't think it would work the way you're claiming it.
Well, you should look into it because Van Bee did it and measured it, and it didn't work that way. And he even did it analogous to a globe where he had an object fixed on the object that was rolling away from it, so it would be angled away, and that didn't produce any emergences either when it's physically at a different elevation relative to the thing occluding it. So
yeah.
And you guys are making the claim here. Why don't you have demonstrations of a virtual image blocking and obstructing an object? Like it's not. You're assuming
text channel. Yeah. A quick answer.
Yeah, I think we can wrap up on that. We've been going for, we got to get to Rob, I guess, but we've been going for an hour and a half, and now we're on virtual images and occlusions, a subject we will focus on for next week. So everyone, for next week, bring your best demonstrations of virtual images occluding light sources. Now, I got Bull Knight, who's going to be getting his tank next week, so he's gonna try and do some stuff to quantify the occlusion of a light source and all that with respect to a physical object in the tank and all that. So we'll be able to put some numbers and stuff to it. But you guys, if your position is that the apparent position of a mountain, which as we just read, I have a website here, right, where I take all these clips of explanations of what a virtual image is and an apparent image, and how light rays don't converge, et cetera, and I just read from it. So we all know that if there's nothing there to interact with it, and it just appears that way, it definitely can't cause an occlusion. So if the mountain is being geometrically lifted up by 2 arc minutes, that 2 arc minutes is going to not actually occlude the light, and the light is going to be visible inside of that 2 arc minutes of the peak. But as was pointed out earlier, It doesn't happen. It gets occluded, basically as soon as it goes into it. So Rob, if you're there, you have some questions or something?
Alan, I've been waiting like 2 weeks. I could probably talk about this with a lot of people, but you seem to be doing a lot of star stuff. And my question is kind of simple, but do you think you can pull up that picture you had with the globe with the happy face on it? Like it was like your first image, yeah. So let's say you're just a human being standing on the top of that water ball, and then
Yep.
you've got your celestial, the not the celestial, but the equatorial plane, right? You're the little dude standing on the top, and then you have the equator about 39, 59 miles below you, right?
Yep.
How how are we seeing the stars 180 degrees apart from each other on the equatorial plane if we're the little guy on the top of the dome?
Our
Like, how do we
vision
see those
of
stars? Like, I
yeah,
don't understand how we even see 180 degrees of the sky.
yeah, our vision is basically an entire hemisphere. You can think of it like, so if you were at the equator, Polaris would be at 0 degrees. So all they've done is just map out like the lengths at which you can see something, and then that, you know, when you move away from it, how it changes angularly. And they did it within a specific uh band, a specific optical band. I think from like 30 degrees to 70 degrees, there's a linear relationship where it's pretty close to 60 nautical miles per degree. And that's the base of it. So all they did was just take how we see naturally and kind of turn it into a coordinate system by taking the linear portion of it and making it symmetrical and then mapping stars to it and deviations from it.
Yeah, it's so weird because you just brought up the putting somebody on the equator. Like, technically, we go 90 degrees from that. Somebody on the equator, technically, shouldn't they be able to see Polaris and the Southern Cross at the same time?
I don't think so. I'm not for sure on the Southern Cross
Well,
thing.
if you look at the diagram, like if
Believe
you're
it's
if
possible
you
to see both at the same time. I think there are probably some photos of it. Like they're both very close to the horizon, obviously, but I think it's possible.
No, the Southern Cross is 20, 30 degrees away from center rotation. You guys
But yeah,
need to
sorry,
check your astronomy.
Sigma Octantis, whatever that southern star is. I think it's possible to see both.
whatever the closest South Pole star would be is kind of what I'm getting at. Then I guess I don't know. Is there a globe
Yeah,
explanation?
yeah, it would be possible to see both of them at the same time. If there was, if they aren't perfectly in the center of the poles, but let's just assume they are for simplification. In that case, they would be perfectly on the line of the horizon. So the horizon is basically cutting through the center of them. If you were at the sea level, but because the horizon drops with altitude, if you went enough high, the horizon will drop enough to like reveal the image of what is actually slightly below the horizon, below the horizontal. So you would be able to see them from some higher altitude due to the horizon drop.
Yeah, and you also get about an extra, half a degree from refraction. It's basically the same thing as the Selenelian eclipse, just with north-south instead of sun-moon.
It's basically the same thing.
Yeah, yeah. I don't think the Alan's picture really lets you understand the scale of how small we are, really, right? And for you to think that your tiny little person, oh, the image is gone. Your tiny little person that's on that sphere earlier, like, I don't see how he could see below him. Do you know what I mean?
You don't. It's not
Like,
below
Oh,
you. You just see to the
it is though, because if you're on the top of that, that's perfect picture you got up right now. If you're on the top of that ball, the equator is 39.59 below you. right? And that plane, how are you seeing anything on that plane when you're like the tiniest little dot on that ball? You think you're seeing 3959 below you way the fuck out there?
Yes, that's specifically
This
exactly what they mapped it to for that.
the celestial equator is not the same thing as the equator on the Earth. You're not seeing people standing like on the equator on the Earth. Those countries that are on the equator, you're seeing the stars. That's
Embo, that's not even what Embo. That's not
Yeah,
even what
no,
he's.
it's not.
That's not even what he's
Yeah.
talking about.
then
Dude,
why did he say
dude,
so-
why is it that you always try to answer something and it's literally never related to what was just previously
Never
said?
look, never know.
That's
Don't
so.
have to. Don't
That's
worry.
so crazy. You just said an entire thing that was absolutely unrelated to what he said.
Yeah, I don't even know if he could steel man what I'm talking about.
That's crazy. But no, so all they're doing, right? You just see in the hemisphere of vision, all they're doing is saying that the reason that the stars are changing place angularly is because of the ball, right? It's not that they're seeing like around the side of the ball. They're saying that what you see horizontally outward from you is changing physically because of ball, because of that relationship to the equator from, your position.
Yeah, it's just because you'd have to. It's just so weird to me how the ball works and the sky works, and we see like apparently we see 180 degrees of the sky, but we would have to look down 3959 to see out
Nah,
that far.
So instead of looking down, right, because their stars are still above you either way, it's their angular change. It's the reason that they're that low in the horizon versus being at your 90 because of that relationship. You're not looking down at them. You're always looking horizontally. All they did was take the curve of the sky and then just say that you're standing on the exact same curve, essentially. And that's why you see it that way. That's all it is. I don't know how to better
Yeah, that's so
explain it.
weird. I understand what you're saying, Alan. I just when I think that I'm on the top of the ball, I don't understand how I'd be able to see 180 degrees of the equator celestial sphere. Yeah, no,
All right,
yeah, we
lads,
have to assume that.
we're gonna go ahead and wrap up for this one. So,
Yeah, thank you,
our
Alan. That does help me. Thank
no
you.
wor
I
no wor
appreciate it.
no worries, lad. So for next week, we're going to do we're gonna focus in on apparent images and occlusions. So, like I said, bring your best citations and demonstrations or examples, etc., to prove your point, and we'll go over them meticulously. But as it stands, Embo, special shout out to you. You did agree about the refraction amount being having to fully be considered. So that's awesome, and I completely agree with that position. And again, our position is the raw geometric intersections, not considering after the effect corrections or making adjustments or whatever. Just the raw plain trig to it makes the correct prediction in every single scenario. And the difference why the elevations are off when you derive the triangle is based off of the intersection difference at the time of occlusion. So that's the root cause of it for both flat earth and globe when we go to derive elevations. Awesome session, everyone. We'll see you guys next Monday.